This $13 old fan motor from a yard sale or a junkyard can generate enough free electricity to charge a 12V battery bank and run your lights, your radio, and your small appliances every single day the wind blows. It produces power at night when solar panels are dead weight on your roof, and it keeps spinning through clouds, rain, and snow. Yet despite small wind generation being proven and documented since 1887, almost nobody has been told that a scrap ceiling fan contains the same core technology as a $5,000 commercial turbine. It's called a permanent magnet alternator conversion. By the end, you'll know what it is, how it works, and how to build your own. Let's dive in. Right now, if you walk into any solar installer's showroom or browse any government energy rebate page, you'll get one answer for residential energy independence: solar panels and lithium batteries. A modest grid-tied rooftop system, say 10 panels covering about 300 square feet, costs between $15,000 and $25,000 installed. That price includes the inverter, the racking hardware, the wiring, the permits, and the labor. Then comes storage. If you want to actually use your solar power at night or during outages, a single Tesla Powerwall runs about $11,500 installed as of 2024. A comparable lithium-ion phosphate battery rack from a company like EG4 or Solar costs between $8,000 and $14,000 depending on capacity. So before you flipped a single light switch, you've spent somewhere between $23,000 and $39,000. And here's what rarely appears in the sales brochure. The National Renewable Energy Laboratory in Golden, Colorado has documented that standard silicon photovoltaic panels degrade at a median rate of about 0.5% per year. That sounds small until you do the multiplication. After 20 years, your panels are producing roughly 10% less than their rated output. The batteries are a far worse story. Most lithium battery warranties guarantee only 70% of original capacity after 10 years. Some drop below that threshold even sooner, depending on how deeply you cycle them and the ambient temperatures in your garage or utility closet. That means the single most expensive component in your entire setup is losing nearly a third of its usefulness before your kid finishes high school, and you can't fix it. You replace it at full price a decade later. Now think about when you actually need backup power the most. January evenings, ice storms, the dead weeks of November when the sky is a gray sheet from horizon to horizon. A December day in Columbus, Ohio gives you roughly 3.5 peak sun hours. In Anchorage, Alaska, you're looking at barely one. Your $20,000 solar array is producing a fraction of its rated capacity at the exact moment you need it most. Meanwhile, the wind resource across most of the United States peaks in late fall and winter. The Department of Energy's wind resource maps, available free on their Wind Exchange website, show average annual wind speeds above 10 km across enormous swaths of the Great Plains, the Midwest, the Appalachian Ridges, the Great Lakes Corridor, and coastal zones from Maine down to the Texas Gulf. That is energy moving through the air above your property 24 hours a day, 365 days a year. Nobody can meter it, nobody can bill you for it, and nobody in the mainstream energy industry wants you to find out how cheaply you can harvest it. But wait until you see the actual dollar per watt math on this build, because it makes the commercial options look like a very expensive joke. The reason a ceiling fan motor works as a generator comes down to a principle that has been understood since 1831, when Michael Faraday wrapped a coil of copper wire around an iron ring and proved that a changing magnetic field induces an electric current in a nearby conductor. Every generator on Earth, from the massive turbines at Hoover Dam to the tiny dynamo on a bicycle wheel, operates on this same principle. A ceiling fan motor is designed to run the process in one direction. You feed it electricity, the magnetic field spins the shaft, and the blades push air downward. But the physics works both ways. If you spin the shaft mechanically by mounting blades on it and letting the wind provide the torque, electricity flows back out of the motor's stator windings. The motor becomes a generator without changing a single wire inside it. The critical detail is what kind of motor you're looking for. There are two main types inside ceiling fans. The first is an induction motor with a squirrel cage rotor. These require external electricity to create their magnetic field, so they produce little or no voltage when spun by hand. Skip these. The second type is a permanent magnet motor. Inside, instead of electromagnets, There are fixed magnets, usually ceramic ferrite or occasionally rare earth neodymium, bonded directly to the rotor. When the wind spins those magnets past the copper stator windings, you get alternating current output with zero external input. No battery needed to excite the field, no carbon brushes to wear down, just magnets, copper, and the wind. Here's how you tell them apart at the yard sale. Pick up the motor and spin the shaft with your fingers. If you feel a series of distinct bumps or resistance points as it turns, that's magnetic cogging. That's the permanent magnets grabbing at the stator teeth. That motor is a good candidate. If the shaft spins freely and smoothly with no resistance at all, it's an induction motor and it won't generate useful power without modification. Walk away from that one. A typical 4-pole permanent magnet ceiling fan motor produces about 8 to 12 volts of alternating current at around 350 RPM. To charge a 12-volt battery, you need at least 13.8 to 14.4 volts DC. So, at stock speed, you're a little short. This is the point where most beginners give up and call the project a failure, but the fix is straightforward. Dan Bartman, a small wind pioneer based in Colorado, who co-authored the book Homebrew Wind Power with Dan Fink in 2009, documented that you can boost output voltage two ways. First, by replacing the stock ceramic magnets with stronger neodymium magnets, which increases the magnetic flux density across the stator coils. Second, by rewinding the stator with more turns of thinner gauge wire, which increases the voltage generated per revolution at the expense of a small amount of current capacity. Bartman measured that a rewound and remagnetized ceiling fan motor could produce 20 to 28 volts of AC at just 400 RPM. Passed through a bridge rectifier, a simple 4-diode component that converts alternating current to direct current, that gives you more than enough to charge a 12-volt battery bank in a moderate 10 to 15 mph breeze. Now, if you're thinking a little junkyard motor can't possibly produce meaningful wattage, researchers at the Federal University of Technology in Akure, Nigeria, published a study in the International Journal of Scientific and Engineering Research that tested a converted ceiling fan motor rated at 80 watts. At wind speeds between 15 and 20 miles per hour, they measured sustained output of 40 to 60 watts of usable electrical power. That's real, measured, documented output from a motor that costs less than a meal at a fast food restaurant. 60 watts runs a string of LED lights all night. It charges your phone and your laptop. It keeps a 12V radio going indefinitely. And paired with a small inverter, it handles intermittent loads like a fan or a small television. And when you compare the cost per watt, the numbers become almost absurd. A single 60WW solar panel at current US retail prices runs between $70 and $120 before the charge controller or mounting hardware. This ceiling fan conversion delivers the same 60 watts from a total parts investment of $30 to $50 and does it in the dark and in the rain. The solar industry doesn't want you doing that comparison on a napkin. Small wind generation has a lineage stretching back well over a century. Professor James Blyth of Anderson's College in Glasgow built a cloth-sailed wind turbine in 1887 and used it to charge accumulators, the batteries of his day, that powered the electric lights in his cottage. He offered the surplus electricity to the people of Marykirk. They refused it because they thought electricity was the work of the devil. A year later, in 1888, Charles Brush built his larger and more famous 65 wind dynamo in Cleveland, Ohio, which powered his mansion's incandescent lights for over a decade. By the 1930s and 40s, the Jacobs Wind Electric Company, based in Minneapolis, had sold thousands of 32V wind turbines to farms and ranches across the Dakotas, Montana, and Nebraska. These Jacobs units were legendarily durable. Some ran for over 30 years on original bearings. Families powered their lights, radios, water pumps, and washing machines entirely from wind. These turbines didn't disappear because they stopped working. They came down because the Rural Electrification Administration subsidized transmission lines that brought cheap coal-fired grid power to those same farms. The physics hasn't changed one bit since James Blyth's day. What changed is who profits from how you get your electricity. That profit structure is visible in how modern incentive programs are written. The Federal Residential Clean Energy Credit under Section 25D of the Internal Revenue Code covers certified small wind turbines installed by licensed contractors. The key word is certified. A home-built turbine from a ceiling fan motor carries no UL listing, no Small Wind Certification Council rating, and no manufacturer's warranty documentation. It will never qualify for the tax credit. It can't because there's no company filing the paperwork and no installer collecting the markup. Most state-level net metering programs require an interconnection agreement with the local utility, and those agreements demand equipment that meets IEEE 1547 standards for grid-tied inverters. Your homemade turbine feeding a battery bank in your garage doesn't interconnect with anything. It exists entirely outside the regulatory framework, and that framework was not built to exclude you by accident. It was built around products and installation services that generate revenue for manufacturers, installers, and utilities. A homeowner who spends $80 and stops buying kilowatt hours is not a customer anyone in that chain wants to create. And yet nobody is breaking any law by building one. You're simply invisible to the incentive structure because the incentive structure was never designed with you in mind. Let's look at who's actually building these right now. A retired machinist in rural Missouri who goes by the username Terry on the small wind forum at fieldlines.com built a 3-blade turbine from a scrapped Hampton Bay ceiling fan motor. 3 blades cut from 4 in Schedule 40 PVC pipe and a tail vane made from a piece of scrap plywood. His total material cost came to $41. He mounted the turbine on a 20 FT section of 1 and 1 or 2 Schedule 40 steel pipe sunk, 3 FT into a concrete footing and stabilized with 3 guy wires. In sustained winds of 12 to 15 mph, he recorded 14.2 VDC after the bridge rectifier, steadily charging a pair of Group 27 deep cycle marine batteries. Those batteries run his workshop LED lighting and a small AM/FM radio every evening. He's been running this system since 2019. His only repair has been one set of replacement bearings that cost him $6. Terry's system produces about $350 W hours on a good wind day. Over a month with 15 decent wind days, that's roughly 5.2 kilowatt hours. At Missouri's average residential rate of about 13 cents per kilowatt hour, that's 68 cents a month in electricity value. It sounds tiny until you realize his system paid for itself in 5 months, and every watt hour since then has been free. If you want to power, heat, and cool your home off-grid, the Passive House files show you how. Full plans, exact materials, and the honest numbers nobody else gives you. It's not too late to start lowering your bill. Scan the QR code and see for yourself. In the Philippines, the Electrical Engineering Department at the Technological University of the Philippines organized a community electrification project that built 20 small wind turbines from discarded ceiling fan motors for coastal fishing villages with no grid access. Each unit cost the equivalent of roughly $18 in local materials. They documented average sustained output of 35 to 50 watts per turbine in the steady coastal trade winds. Those turbines have been charging cell phones, running LED lights, and powering radios since 2017. The maintenance logs show bearing replacements and occasional blade rebalancing as the only upkeep across 7 years of continuous operation. No inverter failures, no battery management system crashes, no firmware updates required. Just magnets spinning past copper, exactly the way Faraday described it 194 years ago. And here's a number that should make you uncomfortable. The American Clean Power Association, formerly the American Wind Energy Association, represents companies selling residential turbines in the $5,000 to $50,000 range. Their published consumer guidelines recommend against home-built turbines, citing safety and performance concerns, but they have never published a single side-by-side study comparing the output per dollar of a properly constructed DIY turbine against their cheapest certified unit. That comparison doesn't exist in their literature because the result would be devastating to their price structure. A $40 DIY build producing 50 watts gives you 1.25 watts per dollar. A $5,000 commercial turbine producing 400 watts gives you 0.08 watts per dollar. The homemade unit delivers roughly 15 times more generating capacity per dollar spent. That single ratio explains why this technology lives on hobbyist forums and not on store shelves. The cost advantage extends beyond the turbine itself. A commercial small wind system typically requires a proprietary charge controller costing $200 to $400 that only works with that specific manufacturer's turbine. A ceiling fan conversion uses a generic PWM charge controller available for $8 to $15 from Renewable or any of the generic brands on Amazon. Commercial installation requires a certified electrician at $500 to $2,000 in labor for the wiring, permitting, and inspection. The DIY system connects to your battery bank with 10-gauge outdoor-rated copper wire and basic ring terminals, tools you already own or can buy for under $20. At every single step, the commercial pathway includes a markup. At every single step, the DIY pathway uses commodity hardware from the plumbing and electrical aisles of your local hardware store. Here is your materials list. The motor is a permanent magnet ceiling fan motor from a yard sale, thrift store, or online listing for $5 to $15. Blades are 3 sections of 4 schedule 40 PVC pipe, each about 20 in long, cut lengthwise at an angle with a jigsaw to create an airfoil curve. Total pipe cost is about $8. The hub is a standard steel floor flange from the plumbing aisle, about $4 bolted to the motor shaft with a coupling nut. Use stainless steel hardware throughout to prevent corrosion. The tail vane is a piece of thin plywood or sheet metal, roughly 12 by 18 and mounted on a 2FT arm behind the motor to keep the blades oriented into the wind. Material cost is $2 to $3. The tower is a 20th length of 1 and 1/2 schedule 40 steel pipe sunk 3FT into a concrete footing. The pipe runs $20 to $30. 3 sets of guy wires with turnbuckles cost about $15 total. 2 60 oil-beady bags of concrete for the footing run $10. Electrically, you need a 50A bridge rectifier for about $3, a 10A PWM charge controller for $8 to $12, and 50 FT of 10-gauge outdoor-rated copper wire for $20 to $25. Grand total buying everything new is between $75 and $120. Scavenging the motor, the pipe, and the tail material brings you down to $30 to $50. The skill level is basic. If you can drill holes with a hand drill, cut PVC with a hacksaw or jigsaw, strip wire with a pair of strippers, and tighten bolts with a wrench, you have every skill this project demands. The wiring is simpler than installing the ceiling fan the motor came from. William Kamkwamba, who built his first windmill in Malawi at age 14 from scrap parts and bicycle components, and later told his story in the book The Boy Who Harnessed the Wind, proved that formal electrical training is not a prerequisite for building a functional wind generator. What is a prerequisite is patience with blade balancing. If your 3 PVC blades are not close to the same weight and pitch angle, the turbine will vibrate on the tower, accelerate bearing wear, and produce an annoying wobbling sound your neighbors will hear. Weight each blade on a kitchen scale. Shave PVC material with a rasp or sandpaper until all 3 match within 3G. Adjust the pitch angle so each blade sits at about 10 to 15 relative to the plane of rotation. This balancing process takes about an hour and saves you years of vibration problems. One critical warning: avoid mounting this turbine on your roof. The building itself creates turbulent swirling air above the roof line that reduces blade efficiency by as much as 30% and puts uneven stress on the blades and bearings. The Department of Energy's small wind guidelines specifically recommend that turbines be mounted on freestanding towers at a height where the lowest blade tip is at least 30 FT above any obstruction within 500 FT. A 20 FT pole in an open yard clears most fences in single-story outbuildings. The roof is always a bad location for a small turbine, no matter how convenient it looks. Also, avoid motors that are too heavy. A motor from an oversized industrial or commercial ceiling fan might weigh 10 to 15 lb. That mass requires significantly more torque to begin spinning, which means the turbine sits motionless in light breezes that would have a smaller motor happily generating. The sweet spot is a motor from a standard 52 in residential ceiling fan, weighing between 4 and 6 lb. These start producing useful voltage at wind speeds as low as 7 to 8 mm. Now for the honest limitations, because you deserve them straight, this system will not power your entire house. A 40 to 60 W turbine charges a battery bank suitable for lights, small electronics, phone charging, and modest inverter loads. If you need to run a refrigerator, a well pump, or power tools from wind, you need a significantly larger system. That means either a custom-built axial flux alternator, like the designs Hugh Pigott publishes through Scurag Wind Electric, or a commercial unit with a higher output rating. Geography matters. If your location averages less than 8 miles per annual wind speed, a small turbine like this will produce very little usable energy. Check the Wind Exchange wind maps from the Department of Energy for your county before you spend a dime. Flat terrain with open exposure is ideal. Dense trees, tight valleys, and dense suburban housing all reduce effective wind speed at rotor height. Maintenance is low, but it is not zero. Expect to replace the motor bearings every 3 to 5 years. A pair of 6203 double-sealed bearings cost about $6. PVC blades become brittle from ultraviolet exposure over time, especially in the Sunbelt states. Plan to replace them every 4 to 6 years at a cost of $8 in pipe. Guy wires need retentioning once or twice a year. Your total annual maintenance cost is roughly $5 to $10 in materials and a single afternoon of your time. But here's what none of those limitations erase. You built a power generating system for under $100. It runs at night. It runs in the rain. It runs in January when your solar panels are buried under 4 inches of snow. It harvests an energy source that no corporation can own, no utility can meter, and no government agency can tax. And if the motor bearings fail after 5 years, you pull it down, press in new bearings for $6, and you're back up and spinning before dinner. Or you find another $13 motor at the next yard sale and start a second turbine. Compare that to the homeowner who spent $30,000 on solar and batteries and is now staring at a degraded battery bank that needs an $8,000 replacement at year 10 and an inverter swap at year 12. Hugh Pigott, a Scottish engineer who has been designing and teaching small wind turbine construction from his off-grid home on the Scurag Peninsula for over 30 years, has documented output data from hundreds of homebrew turbines built by his students across dozens of countries. His construction manuals, which he sells directly through his website, show that properly built small turbines consistently achieve capacity factors of 15 to 25% in locations with average winds of 10 to 14 mm. A capacity factor of 20% on a 100W rated turbine means 20W of average continuous output. Over a full year, that's 175 kWh. At the national average residential electricity rate of about 16.5 cents per kWh, that's nearly $29 of electricity per year from an $80 machine. The machine pays for itself before its first birthday. Every kWh after that is free for as long as you maintain it. That's a return on investment that no savings account, no solar lease, and no utility rate plan can match. The energy industry does not want you to understand this math because once you understand it, you realize the entire residential energy marketplace is structured around selling you the most expensive possible version of something that can be built from the parts they throw away. The technology is not new. The physics is not complicated. The materials are not rare. What's missing is not capability. What's missing is a system willing to tell you the truth. So here's what I want you to answer in the comments. If you had a good wind site and a $100 budget, would you build one larger turbine with a rewind motor and bigger blades for maximum output? Or would you build 2 or 3 small units from cheap ceiling fan motors and spread them around your property for redundancy? There's a real debate on both sides, and I want to hear which way you go. And one more thing for the skeptics. Hugh Pigott's homebrew turbines have been running continuously on the Scurag Peninsula in the Scottish Highlands, one of the most brutal wind environments in Europe, with gusts regularly exceeding 70 mph for over 20 years. The only maintenance has been bearing swaps and occasional blade replacements. If a homemade wind turbine survives 2 decades of Scottish Highland gales, it can handle anything your backyard has to offer. Look up Scurag Wind Electric and read the logs yourself. Next time, we're breaking down a solar air heater built from aluminum soda cans that a retired teacher in Vermont has used to cut his winter heating bill by 40% since 2016, and the whole build costs less than a tank of gas. If this story changed how you look at the discarded motors in your local junkyard, please subscribe and like the video. We are dedicated to uncovering the history and technology that the mainstream energy industry has tried to bury. Let's build a more independent future together. Our next deep dive into hidden treasures will be opening soon.